Good morning, my dear students. Let's continue the chapter called Magnetism and Matter. What was the last discussion? Variation of magnetic moment. Variation of the magnetic moment, and we are doing the continuation. Now, let's start with the previous case. See, there will be so many cases. What maximum cases will be helpful for the NEET exam, we are just doing. We are not simply stopping with one or two cases. And these are the cases what we are discussing in most of the books will not be available here. Let's start. The previous case what we had discussed. If there is a magnet of south pole and north pole placed like this, and there is a magnet of north pole and south pole is placed in this way. You can see here south and north. What is the net magnetic moment of this combination? The question is what? What is the net magnetic moment of this condition? South to north, the magnetic moment is directed. Imagine it's M1. It is a vector. I can say M1 bar, and whose magnitude is M1. There is a south pole to the north pole. There is another magnetic moment. It's M2 bar is a vector and its magnitude is M2. And these two vectors are inclined at an angle 90 degrees, and you know if it's magnitude M1, if it is magnitude M2, and you know how to find the net combination. What is that? Square root M1 square plus M2 square plus 2m1 m2 cos theta. What is the theta? Theta is angle between the two vectors, that's 90 degrees. What is cos 90 degrees here? So I can say the cos 90 degrees is equal to 0, and this complete term will become 0 here. The remaining net magnetic moment will be equal to square root m1 square plus m2 square. Depends on m1 and m2 values, and your net magnetic moment will change. In most of these cases, the question will be asked like this. If m1 is equal to m2 is equal to m. If these two magnetic moments are same, so then your net magnetic moment will be equal to root 2 into m. What is that m? Value of each magnetic moment. Clear? So this is an application. Similar in this case also. In the last class we had discussed. I am just doing a quick recap here. This is a south pole and north pole, and there is another magnet is placed here. Carefully see. This is a south pole and north pole, right? So its magnetic moment, you can see M1 bar, and another magnetic moment is M2 bar. Here also the angle between the two vectors will be 90 degrees, and net magnetic moment will be similar to this. And the other case, how I can draw, you can see there is a magnet here, and there is another magnet is placed here. Here you see a south pole and north pole. Its magnetic moment M1 bar here, M1 bar is here, and this is south pole and north pole. You can see this magnetic moment is M2 bar here. What's angle between these two? Angle between these two is also 90 degrees. So you can say you will get the same answer. I hope you understand the situation. Let's see the another application. Here comes the little advanced level of applications, right? So what is that? You all know about a polygon law of vector addition. What is that? Polygon law of vector addition. According to this, there are three magnets. One, two, three magnets are placed like this. Each magnetic moment is M, capital M, each magnetic moment. And this is the south pole and north pole, and you can see at each corner unlike poles are placed. I'm writing here, at each corner unlike poles are placed. This is south and north. It's south and north. See here, at each corner unlike poles are placed. Okay. Now, magnetic moments, let's see. It's M bar. This is also an M bar. This is also M bar. This is called the polygon law. Clear? When there is a closed polygon is formed in this way, like a triangle or a square. What I can say, a square also. This is okay. It's south and north, the south and north, the south and north, the south and north. You can see at each corner unlike poles are placed in this way. All the vectors will be formed as a polygon shape with an order. You know, order of a vector's laws of addition. So this is south to north and south to north, south to north and south to north, you can see. In these cases, I can say the net magnetic moment will be 0. What is that? A net magnetic moment will be 0. So that is what the polygon law of vector laws of addition tells. Clear? Now, sometimes each magnetic moment may not be same. In that case, how to solve the questions? Let's check. Here, one more application. Let's take a square concept. This is let us take a square concept. Then the triangle also I'll tell you. I'll not leave any of the application for you. So let's start here. It's south, north, south, north, south, north, south and north. It's M, 2M, 3M, 4M. For a better understanding and easy way of solving this question, I have just taken the considered M, 2M, 3M and 4M are the magnetic moments of individual magnets. So it's a magnetic moment, all the vector quantities, you should remember that. M, it is in this direction, and south to north in this direction, south to north here and south to north here. Now, concentrate on these two. Understand? So this is a vector and this is a vector. You can draw this duplicate vector here. This is a 3M and this duplicate vector I can draw here actually. It's M. So what is the net magnetic moment of these two? These two net magnetic moment will be 2M. 2M will be in which direction? 2M will be in this direction because its magnitude is more and your 2m direction will be like this. Keep it aside. Now focus on these two. It's 4m, 2m. So resultant will be 2m. In which direction? Definitely downward, because this magnitude is more when you are comparing with these two. So 2m in this direction. So these are the two vectors I have. So this is one vector I have and this is the another vector I have. So there is a free vector can be drawn. Finally, I am writing here. So this is 2m and here it is 2m. The angle between them is 90 degrees. And if you find, so the net magnetic moment, if you find the interesting answer, you will get it root 2 into 2m. So simple. Come back to the previous case, first case of today's session. Net magnetic moment when magnetic moments are same and they are inclined at an angle 90 degrees, and net magnetic moment formula is what? Root 2 into m. Here also the same. Root 2 into m. M is the magnetic moment of each magnet. Here magnetic moment of each magnet is how much? At the end of the session, at the end of the numerical, the magnetic moment of each magnet is 2m. So it's 2m and this is also 2m, you can see. So that's why I wrote directly root 2 into 2m. You can also check by using the formula. Parallelogram, law of vector addition formula, you just apply here. You can also check. Clear? Now, one more application, right? My dear students, let's continue the previous application and let's see the last application of variation in the magnetic moment. So what is the continuation here? I'm just taking a triangle. It's very important application here. At South Pole and North Pole, South and North and South and North Pole is here. Its magnetic moment is given m. And this magnetic moment is 2m. And this magnetic moment is 3m. See here. Right? This is the complete system. How I am going to draw? I'm just drawing this into two different systems, in which this is m. See this vector I have drawn. M and another 2m is left here because it's a vector quantity. Okay. And this is m as it is I have drawn. And this is the another vector in which I have taken only m. So how much is left here? It's m is left. Understand? This is one system, plus as free vectors I can draw. This is m and rest of the amount of magnetic moment here, it is 2m. So I have drawn a 2m here. I hope you understand. Now you add this 2m and m, you get 3m. Right? And here nothing. And here 2m in this direction. Already m is taken here. So one m is left. So this is the direction of that m. Understand? Clear? Now you can find the net. See, the net magnetic moment in this case is 0 according to Polygon law. Net magnetic moment is 0. Now we need to find the net magnetic moment here. That's important. Net magnetic moment there. What's the net magnetic moment of here? What is the angle between these two? This is the free vector. So this is head of a vector and this is tail of a vector. You cannot find the angle between them now. Angle between the two vectors, how it was defined. The angle between the two tails when they joined as tail and tail. or the angle between the two vectors when they join head and head. So that's what the vector, you can find the angle between the vectors. Now here, this is the vector I can draw in this way as a free vector. Okay, so this is m, free vector I have drawn here. Now it's a tail of 2m and the same tail of m are connected at one point, and the angle between them is 120 degrees because we had considered it is an equilateral triangle. Okay. Now you can find the net magnetic moment will be equal to square root. What is that? 2m square plus m square. That's what m1 square plus m2 square plus 2m, sorry, 2m1 m2, m1 m2 2 cos 120 degrees. Okay. Now, so the same thing I can write, net magnetic moment will be equal to 4m square plus m square plus, this is also 4m square into minus 1 by 2. What is cos 120 degrees? It's minus 1 by 2. It's 2 2's here. So then I can say square root 4m square plus m square. It's 5m square minus, it's 2 is there, minus 2m square. So you can write the net magnetic moment will be equal to 3m square. So final answer will be root 3m. I hope you understand the point. The last application, in one of the JEE exam, this last application of variation in the magnetic moment question was asked. Again I'm just telling you, in most of the books these applications will not at all be there. So this is the last application what we are going to discuss now. Alright. So you have a bar magnet here like this, a big, huge bar magnet of south pole and north pole, and the magnetic moment of this is M. Right? If I make this into the two parts, one part I have taken here, so this part, whose magnetic moment is M by 2. Half of the part, this one, second half of the part. It's a first half and it is the second half. Second half magnetic moment, it's very clear because how many number of parts you make the bar magnet. So M by N. N is the number of parts. It will be the magnetic moment of each part that we have discussed already. Now, so the other half, when that means the first half, I have just made into like this. Carefully see. The other half I have just made into like this. So that's called a semicircle I have made. A semicircle I have made. Carefully look at the situation. In one of the JEE exams, this question was asked. Semicircle I have made. So this is the south pole and north pole, and this is the south pole and north pole. Alright. What is the magnetic moment here? So this is the magnetic moment, right? It's M. M, or you can say M dash. No confusions at all. So the net magnetic moment will be equal to, because M dash and M by 2 are in the same direction, so I can say M dash plus M by 2. And this M dash finding is very easy because in the last class we have derived and we have proved when you bend a magnet into the semicircular arc or any arc. So what is the formula here? So M is equal to, or you can say M dash is equal to 2M sine theta by 2 divided by theta. If you bend a magnet into an arc in the form of arc, making an angle theta at the center, that arc making an angle theta at the center, magnetic moment of that will be 2M sine theta by 2 by theta. So this is already we have discussed, and we had discussed, I remember we had discussed with an example of theta is pi. In the exam also, in the assignment also I have given this question. So when theta is pi, you can substitute theta as pi. The same way here also, what is theta? So this is the arc. The theta value is pi. Now we can write. So the net magnetic moment is m dash. What is m dash? 2m sine theta by 2. It's sine pi by 2 by pi plus m by 2. So the net magnetic moment will be 2 into, so this is anyway it's 1 and it is m. What is this m here? M is the magnetic moment of this part. This part magnetic moment is also half. Understand? This part is also half and this part is also half. This is the magnetic moment of this part because initially you made this into the two parts. This will have m by 2 and this will have m by 2. Here, because of this you bent into the form of an arc, its magnetic moment becomes 2m sine theta by 2 by theta. So, this m is m by 2 now into sine pi by 2 is 1 and divided by pi. It's cancelled plus m by 2. Alright. So, what is the final answer? Final net magnetic moment. What is remained here? It's m by pi plus m by 2, and if you take common m, and it will be 1 by 2 plus 1 by pi. That's it. Okay, let's discuss one more topic from the same chapter. My dear students, let's look at the last concept and topic for today's session. It is Coulomb's inverse square law in magnetism. We had already learned Coulomb's law in electrostatics. What was that? There is a charge Q1 is here and there is a charge Q2. Both are separated by distance r. And the force of interaction between the two charges, that interaction may be the repulsion or attraction. F is equal to 1 by 4 pi epsilon naught Q1 Q2 by r square, isn't it? So where Q1 Q2 we have considered only the magnitudes, irrespective of the sign and the nature of the charge, we have considered the magnitude only, right? Here the Q1 may be positive or it is negative, or both may be positive, both may be negative, or this is positive or this is negative. So number of possibilities are there while considering the charges. And what is this epsilon naught? It is the permittivity in free space. And you know the value of K, which is 1 by 4 pi epsilon naught, 9 into 10 raised to 9 Newton meter square per Coulomb square. Similarly, in the place of charges in Coulomb's inverse square law of magnetism, we consider the magnetic poles, because magnetic poles also can be considered as negative and positive. I have told you, south pole will be considered as a minus m, north pole can be considered as plus m. M stands for small m, which is pole strength. Okay, so pole strength I am considering here. So imagine it's a magnet have pole strength m1. So there is another pole strength of another magnet m2. Both are separated by a distance r. If this is the north pole and this is also a north pole, and you can say, so the force of interaction between them is repulsion in this way. Okay. If there is a south pole and north pole, the force of interaction will be attraction in this way. No confusions at all. Here, force of interaction will be equal to constant into pole strength, the m1 m2 by r square. Right? So definition I am not writing here. So what is the definition? Orally I am telling you. Force of interaction between any two magnetic poles will be directly proportional to the product of these two poles' strength and inversely proportional to square of the distance between them. That's it. So what is this K? I'm writing F is equal to, the constant will be a mu naught by 4 pi into M1 M2 by R square. It's a final answer. The force of interaction between two magnetic poles. Okay, so a lot of applications are there. In further classes we will be discussing. Now, so what is this mu naught by 4 pi? So mu naught, we know mu naught is permeability in free space. So what is its value? Its value will be 4 pi into 10 raised to minus 7 Tesla meter per ampere. Now, here imagine a situation if M1 is equal to M2 is equal to 1 ampere meter. What is the SI unit of pole strength? Ampere meter. And the distance between them is 1 meter I have considered. In this case, what will be the force if you consider all these things? F is equal to mu naught by 4 pi is 10 raised to minus 7. From where? So from here you get it. So mu naught value is 4 pi into 10 raised to minus 7. 4 pi gets cancelled and you get like this. And this is ampere meter. It's 1. Anyway it is 1. And this is R square. R square is also 1. So you will get an answer 10 raised to minus 7 Newton. Is it okay? Clear? So this is how. When the force of interaction between the two poles having equal magnitudes is 10 raised to minus 7, then you can directly say that your pole strength values are individually 1 ampere meter. Okay. So you know the concept mu R. What is that? Relative permeability. What is this? Relative permeability, which is equal to mu by mu naught. Alright? So mu is what? Permeability in a medium. Here, permeability in a free space. In most of the cases, we get the question related to the permeability in free space. But sometimes you can expect this also. From here, what I can write? So mu is equal to mu R into mu naught. Right? Same force of interaction between the two poles in a medium, you can write in this way. F is equal to, what is mu naught? Mu naught, in the place of mu naught I can write mu, because in a medium we are talking about mu by 4 pi into M1 M2 by R square. So this expression I can write mu is equal to what in terms of mu R and mu naught? So mu R and mu naught divided by 4 pi into M1 M2 by R square. Okay, in a medium you get the expression in this way. In Coulomb's law, you might have solved so many numericals in electrostatics based on Coulomb's law and even based on the null point. Here, one basic question based on the Coulomb's inverse square law in magnetism we will discuss here. Look at the question. The force between the two poles is reduced to x newtons. Reduced to x newtons. It's not reduced by. Reduced to or increased to means a given value is the final value. So final value is x. Reduced to x newtons. That's a force. How many times? Reduced to x newton. Okay. When the separation is increased to n times, right? Initially, so this is M1 and this is M2. So the force is F. Okay. Now, when this separation is increased to initial distance, imagine it's R. When this separation is increased to n times, that means n into R is the distance between these two. Now see, when the separation is increased to n times, so the force reduced to x. So x is equal to mu naught by 4 pi into M1 M2 divided by R square. What is R square here? It is NR whole square. This is equation 1. Okay, already you might have solved so many questions. That's the reason I'm just going with a little flow. Now, from this value, from what value? From this x. Okay, from this value, it is increased by y Newton. Now it is increased by means whatever is the actual value, from that it is increased by y Newton. So this is m1 and this is m2. See, force will increase when the distance between them will reduce. So that is why in diagrammatic representation also I am representing here. So this is x plus y. The force is increased by y from this value. See, clearly it's from this value it is increased by y newtons when their separation is made 1 by n of the original value. So 1 by n times of the original value. Okay. Now, so x plus y is equal to mu naught by 4 pi. So this is x plus y is equal to mu naught by 4 pi into m1 m2 by, what is this here? R by n whole square. Understand? So equation number 2. Now what is the question? What is the question? What is the relation between x and y? That's the question. Alright. So equation 1 divided by 2, if you do it. So equation 1 divided by 2, here itself you can do it. Mu naught by 4 pi, mu naught by 4 pi. m1, m2, m1, m2 cancel. What is remained? Let's write x by x plus y, which is equal to, here the numerator it is 1 by n square r square divided by, here 1 by r by n whole square. Okay. So this I can write x by x plus y is equal to 1 by n square r square into r, this will become reciprocal here and again reciprocal here. So it will be r square by n square. Okay, r square cancel and it will be 1 by n square into n square, it's n to the power 4. Right? So now this will be, this is LHS and this is RHS finally. Just cross multiply here. N to the power 4 into x is equal to x plus y. Okay. The question is relation between x and y. So this is x and this is x. This x, let's take to the left hand side. N to the power 4 into x minus x is equal to y, and from here x, if you take common, it will be n to the power 4 minus 1, which is equal to y, right? When you are, in the basic mathematics, when you are finding the relation between two variables x and y, so both must be in the opposite sides, so left hand side and right hand side. So if possible, x and y. Understand? Clear? So this is how the basic concepts and some advanced concepts we can learn in terms of applications, and we will be focusing more on the topic called magnetic field in the next class. What was the topic here? A magnetic field in the next class. While discussing moving charges and magnetism, we had discussed a little about magnetic field. Now, with more details, the magnetic field will be discussing, right? So, my sincere suggestion to you is, when you're coming to the next class, just revise the magnetic field concept, magnetic field lines around a bar magnet concept. You just revise and come back, right? All the best.